Acceleration number 5. This is more practice, exactly the same thing you were doing with acceleration number 4. So let's get started. I'm going to do the same things. I'm going to make a little picture. I'm going to list out all my quantities. I'm going to write down the equation that I'm going to use. And let's see if I have that equation sheet in my pile. I know what they are. Do you? You don't need to memorize them. Let's see. Oh well, I'm just going to drop them on you, I guess. Let's see. We got a skier starting from rest. Skiing down a slope. From rest, that means the initial velocity is 0. You got to pick up on that. And going down the slope, there's the skier. Skiers kind of lean forward like that, right? They got the little poles. Oh, that's pretty good. Acceleration is 1.6 meters per second squared. And what is her velocity after 15 seconds? So what is her velocity? I don't know. After 15 seconds. Okay, so I'm going to make my list. I've got acceleration. I have initial, final velocities. I have the displacement, and I have time. All right, so what do we know? The acceleration, initial velocity 0. I'm looking for this, and I know the time. So not using that right now. So for part A, what equation does not have delta x in it? It's the one VF equals AT plus VI. And VF is what we're looking for. Again, I'm not going to write units in these when I'm doing my math here. And 1.6 times 15 is 24. All right, that's part A. How about part B? How far? Saw that coming, right? So that's this, not that one. So which equation does not have the final velocity? That is this one. So delta x is equal to 1/2 a t squared plus VIT, that's 0. That's 15, so that's gone. So we got 1/2 times 16, oops, times 1.6, just kidding, times 15 squared. That's 180 meters. All right. Getting the hang of this, huh? Truck traveling at a velocity of 32 meters per second due east. Pretend that this is east this way. Traveling 32 meters per second. It's about 70 miles an hour. Comes to a stop by decelerating. Decelerating. If you're going to make this velocity smaller, you're going to have to do that with a negative acceleration. And we're going to come to rest. So this is the initial velocity. If we are stopping, problems about stopping are pretty common, so we need to get used to if something's stopping, that means its final velocity is going to be 0. So here it's going, and then here it is stopped. All right, nice picture. Thank you. I'm going to make my table here. Acceleration, initial, final, delta x, time. And I know the acceleration, initial velocity, final velocity. How much time? I mean, you can set up the equation. I want to encourage you just for a second to look at this and see if you can figure this out without doing a whole lot of equation writing, just thinking about what acceleration is. Acceleration tells you what happens to the velocity for every second that goes by. So this means the negative 8 meters per second means that every second that ticks by, you're going to subtract 8 from this. And 32 is a multiple of 8, so you're going to have to subtract 8 4 times before you get this down to 0. So that time's going to be 0. Now, you don't have to do that, of course. You can use the equation, but I just want to show you that that's what happens when you use the equation. Final velocity is 0, acceleration is negative 8 times time plus 32. So you add that over, divide by 8, and sure enough, you get 4 seconds. That's the answer for part A. Put little boxes around those. For part B, we want the delta x. Oh, this is the wrong equation here, isn't it? We want this one. So the VF is 0, the initial is 32, plus 2 times negative 8 times delta x. Algebra happens, so I'm going to move this to the other side. That's 32 squared divided by negative 16. Of course, that's going to be negative on the other side, so I should get a positive answer. It wouldn't make any sense for the answer to be negative anyway. So 32 squared divided by 16 is 64. 64 meters it takes the truck to stop. All right. Number 3. Car's traveling at 16 meters per second when it begins accelerating. So it's already going. Look, there's my car. How about that? It's a nice car. So it's going at 16 meters per second, and then it starts accelerating faster. And after traveling a distance of 105 meters, now it's going 26 meters per second. Now the car, I started to draw a bigger car. That doesn't make the car bigger. It's still the same car, same size. It's going faster. That's what those little lines mean. 26 now. How much time does it take for the car to travel that 105 meters? All right. Let's see what we got. See what equation we need to use. What's the acceleration? I don't know. The initial velocity is 16. The final is 26. And this is 105. So how much time? So that looks like this equation. Haven't used this one in a little while. All right. So what's the average of 16 and 26? Pretty sure that is 21. So 105, let's say 5 seconds after you do that algebra there. And for part B, that was the time. Now we're going to be looking for the acceleration. So that looks like our VF squared equals VI squared plus 2A delta x. So VF squared so let's see, 26 squared minus 16 squared. I'm going to show you how I'm going to do this on my calculator. If you've got one of these fancy calculators, you should do this. Get it to do a little fraction. I'm going to have 26 squared minus 16 squared on the top, and on the bottom, 2 times 105. Oops. 2 times 105. Yeah, that's a nice way to do it. There's no reason to just to do one calculation at a time and keep hitting enter. That's 2. Acceleration is 2 meters per second squared. All right. Number 4. Suppose the driver of a car traveling at 15 meters per second sees a traffic light suddenly turn red. I'll put the light over here. All of a sudden, it turns red. That's the one on the top, right? The red. And driver is going 15 meters per second. The reaction time of the driver is 0.75 seconds, which is the time between the instant that he sees the light and the instant the brakes actually start stopping the car. So that means for a time of 0.75 seconds, the car is just going to keep going at a constant velocity of 15. So that's like a little throwback to Unit 2, right? So it's kind of its own, like, not hard, but a little separate baby problem there. And then when we get to here, after that 0.75 seconds, I don't know how far, what distance I traveled there, but I'm still going to be going 15 meters per second. And then car is going to start slowing down. If you're going to slow this velocity down, then you're going to have a negative acceleration. Oh, I don't know, I put a 5 there, sorry. Just 6.2 meters per second squared, negative. And we want to know what's the total stopping distance of the car. So we're stopping, hopefully somewhere near the red light, with a final velocity of 0. Okay, so this part, we can do all that, right? Acceleration, initial velocity, final velocity, delta x, and the time. But that's only for this part, right, after the brakes are hit. So I can go ahead and fill that stuff in. My initial velocity would be 15. Final velocity, we're stopping, so that's 0. The acceleration is negative 6.25, 6.2. Really want it to be 6.25. And stopping distance, I'm looking for this. So I can set that up. It's going to be that equation again. I can do that. But what about this? So what's happening here? Well, with constant velocity, the mathematical model that we have is displacement is equal to velocity times time. There's no acceleration, there's no initial and final velocity because velocity is constant. So this was from Unit 2. Displacement is equal to velocity times time. Let's see. The displacement is equal to the velocity, 15 meters per second, times the time. I usually drop my units there. I don't know why I didn't there. It doesn't matter. We'll be okay. You can see the seconds canceling out. We're going to get meters. So 15 times 0.75, 11.25 meters. It should make sense to you that if you're going 15 meters per second and you do that for a little under a second, if you did it for exactly 1 second, you'd go exactly 15 meters if you're going 15 meters per every 1 second. So if you do it for a little less than 1 second, you're going to go a little less than 15 meters, right? So that's how far the car goes during the reaction time before the brakes get hit. How about over here? I got 0 is equal to 15 squared plus 2 times negative 6.2 delta x. So 15 squared divided by 2 times 6.2 is 12.4. That is delta x of 18 point, let's say point, what did I keep over here? Let's say 0.15 meters. I'll keep to the nearest hundredth. And then the total stopping distance, I need to add those together. So what is that, 29.4? Right, that's how you do that.